go ahead and record this. Just make sure everybody's, just want to make sure nobody's saying they can't get in. There's nobody. All right, I don't know where everybody is. Okay. So let me move things around on the screen and then we can begin. Sorry, I'm fighting with Zoom to make things I don't want go away. All right. So first off, changing units or talking to barbarians. Okay, and some of this I think you might have done with Tim in statics, but just to be sure, let's go through it. Let's first talk about the metric system. And let's go over, can somebody tell me quickly, what is the relationship between, first of all, what are the units of force? And what are the relationships to units of force and other units in the metric system?
Does it use newtons for the force?
Right, so we have the units of force, or newtons, and what is a newton equal to? If you don't remember, go back to Newton's second law. F net equals ma, and then in the metric system, we just plug in 1 meter per second squared for acceleration, 1 kilogram, and that just becomes the definition of Newton, 1 Newton. So we get 1 Newton equals 1 kilogram meter per second squared. And so when we define these units in the metric system, we just insert unit amounts, 1, and that becomes our definition. All right. That's not how barbarians work. Okay. Barbarians lack the foresight to imagine just the cornucopia of possibilities, just how many things we could study. And so they build units around the most common interaction they see every day, namely gravity. So I should say specialize units for gravity. Did Tim talk about this in statics?
We went over stuff like slugs and pound force.
Awesome. That's exactly what we're going to do. So, all right, I'm going to do it then, just so I can say I showed you, but you guys have seen this. Awesome. All right. So the way it works in the English system is, it turns out we're going to have 2 units of force, but the one that people usually talk about is a pound of force. And the way it's defined is not based upon just unit amounts, it's based upon gravity in barbaric units. So we say 1 lbf, 1 pound of force, equals F, and it's still F equals ma, but instead of choosing acceleration of 1, we're going to choose gravity, the gravitational acceleration on the Earth's surface. So the mass is going to be 1 lbm, 1 pound of mass, and the acceleration we're going to have is 32.2. Really, it's like, it's got a whole decimal thing, 32.17, blah, 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 feet per second squared. That's gravitational acceleration in feet units. And so the statement is 1 pound of force is the gravitation is the weight of 1 pound of mass. So 1 pound of mass causes a weight of 1 pound of force. So sometimes people say, oh, 1 pound of mass equals 1 pound of force. That's not right. It causes 1 pound of mass causes 1 pound of force. They're not equal. They have this stupid factor here, right? And you can't forget that. Okay, so I apologize. I'm trying a little different program to do the notes other than Zoom. So we'll see if this works better. In fact, you can turn it around and say just rewrite this. You can say 1 lbf is 32.2 lbm, pound mass, feet per second squared. Or another way that's useful is to, you can set up unit ratios just to say 1 equals 1 lbf over 32.2 lbm feet second squared. Okay, so I'm just doing kind of physics 1 unit conversions here, but it's important to know where they come from. So did Tim go through? You guys did examples like this with Tim? Is that right?
Yeah, we did a couple.
Okay, are you guys confident with it, or should I do one? Or should we fiddle around with it?
I don't know. We should probably do one because we haven't done them since like the first week.
Okay. Okay. Convert 1 lbf, 1 pound of force, to the metric system. So first thing you have to do is ask, what does that even mean? We know what's the thing we talked about in physics 1? We said that 1 pound equals what? Michael, you haven't said anything. What does this equal? 1 pound equals, what do we say in physics 1?
14.4 newtons.
Well, that's not what we said in physics 1. I had you learn 2.2 what? Kilograms. Right? That's what we had in physics 1. So what kind of pound was this necessarily if it was related to a kilogram? Well, if it's related to a kilogram, this has to be lbm. All right, so we can make a unit ratio. Basically, we can say 1 equals 1 lbm over 2.2 kilograms. So now the goal is to convert 1 pound of force to its metric equivalent. This is a pound of force, so you can't use this 2.2 number because that was relating masses. We have to be sure to talk about pounds of force, and therefore its metric equivalent would be newtons. Okay, so take a second. Let's see what's useful. I think I'll leave it there. Take a second and convert those to pounds of force to newtons. All right, for those of you who missed out on that whole discussion, because I am still incompetent with Zoom, months and months into this whole thing, let me recap, and then you'll at least have some formulas. Hey, Gabe. All right, first off, I screwed up the unit conversion here. So go back. This is where I left you guys before I stopped recording. And I had the units upside down because I was talking and I wasn't thinking. So I fixed it here. And then what we did is we just laid out, like you do in chemistry or any other class, how to convert from pounds of force, try to cancel the pounds of force and try to end up with newtons. And so basically we just canceled the pounds of force and tried to replace everything with its metric equivalent. So I use my unit ratio here to cancel the pounds of force, and then I cancel the pounds of mass to turn them into kilograms. I cancel the feet to put them into meters, work it all out, and I got 4.4 newtons, which according to Google was correct. Okay, so I'm going a little fast, but if you're watching the video when I post it here on YouTube, you can pause it and work that out. Then what I did is I went through what slugs are. Slugs are what happens when barbarians think. So it's really what you do if you were to use barbaric units, but kind of define composite things like you would in the metric system. So just like we said, 1 Newton is 1 kilogram times 1 meter per second squared. A slug is the unit of mass, which plays the same role for barbaric units, for English units. And then you can go through the conversion here. We know that, so that says 1 pound of force is 1 slug times 1 foot per second squared. But it also is related to pounds of mass using this 32.2 factor. And I just divided these two equations to find that the ratio of a slug to a pound is determined by this 32.2 factor. So, all right, for those of you who watch this video and are confused, just pause it and work through it. It's just simple algebra. All right. For those of you who are here, is that pretty much what Tim did in statics? It must be.
Yeah, well, like he showed us it like for a second, and then just basically gave us the conversion factors, and was like, "You're probably going to need these."
And to be honest, that's that's fine too. Right? You guys should know this on a test. I will give you the conversion factors for the stuff you need. Okay, so. Well, in fact, on the tests, I'll ask that you bring the textbook because it'll have the appendices with all the properties that we need to know. And on the back cover of the book has all the conversion factors. So there's no way I can really police, do you have the factors anyway? So, it's kind of good to know, is a slug bigger or smaller than a pound? That's really the key thing to know. All right. Okay. So that is what I wanted to do on units. I wanted to say a few words about ways to write the first law. Okay. So, Gabe, I'll pick on you since you just showed up. Can you tell me what is the first law of thermodynamics? We've talked about it a couple times.
All right, 1 second. I have it written down.
You got to know it.
Um,
Burned right in your forehead.
yeah, I probably should.
Yeah, you really should.
All right, I'm blanking.
Okay. So.
No, conservation of energy.
Yeah.
Heat minus work equals change in energy.
Awesome. Yeah. And I'll write out the full thing. So there would be kind of macroscopic kinetic energy potentially, plus maybe some macroscopic, like gravitational potential energy, something like that.
Yeah, I had that written down on the next line.
That's fine. Yeah. A lot of times people drop these because for most of our systems, or many of our systems, these are negligible. Plus the change in U. I don't know. Brian, what does U mean?
It's the internal energy.
Internal energy, yeah. There are going to be a lot of vocab words here. We got to be really solid on these. So I'm going to be quizzing you guys. All right. Internal energy. that equals, and then Gabe said Q. Well, what was Q, Gabe?
Heat.
And minus W, which is work. We know that. All right. Now, I gave you, so we talked about that. And like I said, many times these first two are negligible. Now, let's talk about these. Is kinetic energy intensive or extensive? What do you think, Michael? If you have a small car or a large car, what happens to the kinetic energy?
It increases because of mass.
Yeah, so it's proportional to mass. So this must be extensive. And similarly, potential energy is, MGH. That's extensive. Internal energy, that's the energy inside the volume in all little molecules you can't see anymore. That's going to be extensive as well because it scales with the number of particles or the amount of mass. Heat is going to be extensive as well, and work is going to be extensive. These are all extensive quantities. So this is the extensive way to write it. All right. How can I take an extensive quantity and make it into an intensive quantity? There's not one way, but there's a common way that engineering, our textbook that will do. How could you do that? Alex, how could you do that? How could you take an extensive thing and make it intensive? Well, okay. Start with volume. That's
Right.
extensive. What's a close cousin to that is intensive? Can you be very specific when you tell me?
Density.
Okay. There's a better one. Really closely related to that, though.
Mass.
No. What's related to volume? Very specifically. Can you tell me a really specific answer that's related to volume?
Specific volume.
Yeah. All right. Yeah, that's good. All right. So that was the volume divided by the mass. All right. Now you said density, which is 1 over that. I would say that density is kind of like an intensive version of mass, whereas specific volume is an intensive version of volume, as I think about it. So we won't use density very much, to be honest. Sometimes problems will state the density, but most of the time we will work with specific volume, in all honesty. Okay, why is this intensive? Well, it's the ratio of two things which scale the same way. So if I change the numerator, the denominator changes by an equal amount, and the ratio is independent of that. Okay, so that's one thing. A chemist would divide by the number of moles, but we're not chemists, at least not in this class. So we're going to rescale these quantities by mass to make it intensive. So an intensive way is going to just be to divide everything by mass. So I'll write that down. So I just say that's just going to be delta KE over mass plus delta PE over mass plus delta U over mass equals, and sometimes the book writes capital Q over M, or sometimes so I'll start with that. And then the book, so notice these, when we talk about the energy formulas, all of these extensive forms of energy are written with capital letters. When we work with the intensive quantities, the book will use lowercase. So this is just equal. These just become, it's delta lowercase Ke plus delta lowercase pe. It's just notation, right? Just lowercase is going to be the intensive version. Capital is going to be the extensive version. Oh. Okay. And this will be lowercase q minus lowercase w. Are there questions on that? I usually try to exaggerate or make sure it's really clear what I've got. To be honest, what I normally do when I've got like a u is I make it kind of like a script quantity, like I do with the volume. I kind of make it a script thing. And then w's I'll probably do like a cursive w. All right. So what would that mean? Well, delta lowercase ke, that's just going to be the kinetic energy divided by the mass. That's just 1/2. Velocity. That's actually speed squared. Delta pe lowercase is just going to be, well, it would be, if it's gravity, it's mgh. That's just going to be g times delta h. Okay. So hopefully, so don't get confused by that. It's all I'm doing is just working with intensive quantities. And for example, in the back of the book, it's the lowercase quantities, which are in the tables. And then, so it's the intensive quantities. And then if you know, say, the lowercase quantities, you can go back to the capital quantity just by multiplying by mass. So it's easy to reinstate the overall size by just multiplying by the overall mass. Are there questions on that? It's just notation, but it's what our book uses. All right. So you have to read the questions very carefully. I can tell you there are lots of times where you read it, you'll know what to do, you dive in the problem, fine, and then you'll realize, oh, crap. They didn't give me volume, they gave me specific volume, and that means you've got to do a bunch you got to go back and convert things, or maybe they give you the extensive quantity, but the answer they want is intensive, and so you got to do some conversion. So just read things carefully. There's just a potential to assume everything is the extensive quantity and just ignore the units, basically. If you watch the units carefully, it's clear, because this is the lowercase letters or quantities will always be per kilogram. So for example, the units of u, lowercase u, is going to be joules per kilogram, or usually the book uses kilojoules per kilogram, right? So because it's an intensive quantity, it's per kilogram. So if you follow the units, it's clear what's going on. But if you're not careful, it's easy to mess that up. And I've done it lots of times. All right. Is that okay? Can I get a thumbs up if that's clear? All right, all right, all right. I think Brian will have that. Okay. Other things. Let's talk about baby steps. All right. So the way I wrote the first law, either with extensive form or intensive form, is with deltas, big changes, macroscopic changes, measurable amounts. That's fine, but for a lot of derivations, it's useful to have write expressions with baby steps. Now, that sounds really easy, and it's not too bad, but we have to be a little careful. So normally, when we want to go from kind of macro to micro, you basically just change deltas to D's, or for differentials. Okay, that's what you would do in a math class, for example. Here it's just a tiny bit more complicated. So for some things, it is that simple. So for example, if I had a baby step in kinetic energy, that would simply become, for a baby step, it's just going to become d KE. Right? We won't use that very much, but that's what it would be. A much more important one, though, for us will be the change in internal energy would become du. And similarly, if I had intensive things, I would have delta lowercase u becomes du if I'm thinking about little baby steps, little small changes. All right. So here's the thing. Pick on somebody. Brian, Gabe, Alec. I think Michael. I think you're up. All right. If you have a baby step in calculus, imagine you're integrating some curve, and you integrate. So okay, actually, let's do something really simple. You have a graph, and then we have it's a flat graph, and we're going to integrate from here to here, and the width of this is dx, and the height is going to be, a constant. Okay. How would you find, what would be the area under this curve if you integrated from state from 1 to 2, from left to right?
C times dx.
Awesome, rock star. Okay, so that's from 1 to 2. Okay, Michael, if you were to integrate from 2 to 1, what would the area be?
Just be the opposite sign.
Awesome. So if you were to go from 1 to 2 and then back from 2 to 1, what would be the area under that curve?
0.
Okay. Now this is for differentials, but it worked the same. Now, oh, so incidentally, the name for this, for a quantity, such that if you integrate it around a closed loop, it's called an exact differential. A differential which integrates to 0 around a closed path, let's say. Okay. So around, in some sort of, as long as you're integrating from here to there, and then you basically start and finish at the same place. Sorry, not a closed path, around for any closed path, right? Is called an exact differential. That's a math word. You will learn all about it in DiffyQ. Did anyone take DiffyQ last year, Alex? Did you do that?
No, I haven't had that.
Okay. So when you take differential equations in the spring, you will learn about this. It'll come up in Calc 3 too, but I think not until the last little bit of the course. But what it will mean for us is that if you start at one place, go somewhere, and then come back, and the total integral is 0, all for any, regardless of the path, then it's exact differential. All right. Now, okay. And when we have something which is an exact quantity, we use D's. D for changes in exact quantities. Okay. Now, I know it probably sounds like I'm talking about a bunch of weird random stuff. What the hell does that have to do with anything? Okay. Think about the formula for work. It's the formula for work is the integral of force. Let's talk about physics 1 stuff. F dx, right? Now, what I want you to imagine is, I have a table with friction, and I push a block from point 1 to point 2, and then come back to point 1. So I go over and back. Okay, and we can ask how much work was exerted by friction on the block. Is that 0? Gabe, what do you think?
No, I don't think it's 0 because the friction is in both directions.
Yeah.
It's not negative friction.
Friction doesn't give energy back. not mechanical energy, right? It steals energy both ways. So you lose going forward and you lose coming back. So that means that this thing that I'm integrating, when I integrate there and back, doesn't add up to 0. Therefore, this is not exact. We call this so we say that for friction, F dx is an inexact differential. Now, I chose friction because it's familiar and we kind of know the answer. It turns out most of the time, unless you know something special, work is inexact. So for us, work is going to be associated with inexact differentials. You lose and you lose some more. Now, special machines, you run things in a special way, blah, 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 special, maybe it becomes exact. But if you don't know anything, you should assume it is inexact. And the same thing is true with heat, right? So heat is the same way. Occasionally it might become exact, but usually it is inexact. It doesn't, you lose and you lose some more, all right? So because of that, we need some way, we want to talk about baby steps. We want to talk about little changes in kinetic energy, little changes in internal energy, little amounts of work, little amounts of heat, and we need some way to indicate that it's different. So for inexact quantities, so we will introduce an inexact differential. And I'm going to use the book, what the book does, and it's a common definition. And I'm going to use a delta instead of a D. There are other books, and it's quite common, where they use a D with a line through the top. I won't do that because it's be too easy to forget one. Deltas are easy for me to remember. So how does this play out? Let's write down the first law of thermodynamics.
Is that basically just a partial derivative?
No.
All right.
Yeah, no. What? In class next week, I'm going to show you a difference. I came up with a demonstration which kind of explained what's going on there. Here's the way to think of it. Okay. The things which are properties, the things that are exact over here, these things are all properties of the system. So if I reverse the system, those things just go back to where they started. Full stop. But with work and heat, those aren't properties of the system. They depend upon details with the environment. And so what happens is, even if you try to reverse the system alone, generically, that doesn't change. The environment is not reversed. And so therefore, just reversing what happens in the system is not enough to unwind the process backwards. Does that make some sense, Brian? So,
yeah, I guess.
So the idea is the properties of the system only depend upon the system. So when I walk forward and then walk backwards, it just unwinds. But when I have heat and work, they depend upon all the rest of the details in the universe. And so just walking backwards, having the system walk backwards, is not enough to reverse those. You would have to reverse everything in the universe in general to unwind those. Unless, coming back to my earlier caveat, there's something very special about the type of process. There are some special processes where unwinding the system is enough to reverse the work, and then it becomes exact. Or the heat, same thing. I mean, that's a special case. So I kind of have a little demonstration. Basically, last year I kind of had this idea. I tied strings. I had a balloon, and I had everybody kind of hold us with many strings off of it, and we kind of had everybody pull their string, and by defining the system, or by different groupings of strings, you could come up with reversible processes or irreversible processes and things like that. And so maybe that'll help. Anyways, so the first law of thermodynamics is going to be stated like this in differential form. Okay, with in extensive form, it's going to be d ke. Usually, if we're talking about this, we won't write this, but today, since I'm writing it all out, I'm going to. But usually we would drop this. dpe plus du, because if I unwind the system, these things all go back to where they started, so their changes all flip signs. And on the right-hand side, we put all of the interaction stuff somewhere up here. Got it written down. Q and W stuff. Okay, so that's going to be delta Q minus delta W. So the way you read this is you say the differential change in the kinetic energy plus the differential change in the potential energy plus the differential change in internal energy of the system, all of these are of the system, equal a differential amount of heat minus a differential amount of work. Notice the change in language there. Here I'm talking about of the system. I use the prepositional phrase of the system because these are properties. And here, I can't think of heat as a property. It's not of the system. I just say it's an amount. It's just like a lump of energy. And it's a small lump of energy. So I say it's a differential amount of heat. Okay, that's the way we would say that. All right. Now, you can still do calculus and integrate these up in the same way. But just know that it's kind of like evaluating the work due to friction. You have to think about each path separately, because usually going forward is different than going back, and they don't just add up to 0. But you do normal integral rules and stuff like that. Or, oh, sorry, this is differential, and these are extensive, or I can write it with intensive. So this would be first law. So this was extensive differential form, and this will be intensive differential form. And it's going to be D. All right, it kills me. All right, not kills me, but just tedious. These will almost never be significant when we're doing all this stuff. D PE plus D little u equals delta Q minus delta, W. And typically, in fact, I'll just write D little u is delta Q minus delta W. That's usually how I will write this. Is that okay? Raise your hand if you're confused as to what these symbols mean, or what the intuition behind them is. I'm going to tell you what they are here in just a minute. Okay, Alex, you're confused, or you're okay?
I'm thinking I'm pretty okay.
All right. So let me give you the useful formulas here. For boundary work, we get a little bit of boundary work is, well, that was the so boundary work was P dV, or sorry, the integral of P dV, sorry. So this is just going to be the integrand of work, the boundary work. Or in intensive form, this would be P d specific volume, because when you divide this by mass, it becomes specific volume. All right. So when it comes time to actually evaluate these changes, this is the formula that we actually will use. And this is familiar stuff. So when I write it like this, it's true, but it's all very abstract. Whereas when I talk about pressures and volumes and stuff like that, then it's concrete and you can imagine what's going on. There actually are some other forms of work that can come up. The most important one is associated with electricity and electrical charge. It turns out for electrical charge, then we're going to say that del W equals, it turns out you need a minus sign because of our sign convention. It's reversed from the what you might usually call it in linear circuits. And it's going to be so the book writes it as the EMF times the charge. And I'm going to write this dq, even though the book uses dz. The book says minus so this is the charge. And this is the EMF, which has units of volts. Okay, so does that look familiar to you guys from linear electrical circuits? Does it almost look like something you've seen there?
No.
Oh. What if I said P
Power.
IV?
Yeah.
Yeah, V. Okay, V, you're talking about the voltage drop across, or that could be an EMF. And I, what does I measure?
Current.
Current. Yeah, what's that? That's charge
Charge per unit time.
per time. It's dq dt. And what's power? That's energy. It's the power delivered, dw dt. So notice the thing you're learning about in electrical circuits is exactly this if you divide everything by dt. Okay, it's really the same. In fact, we're going to use, I'm going to use that just in a second here. But okay, so that's where this is coming from. We won't use this very much. There's just a few examples where it comes up. The book has some other ones involving dielectric materials and polarizing materials. That isn't going to be an issue for us. So they put it in there, I guess, for completion, but we aren't going to do that this semester. I will talk about that kind of energy in electricity and magnetism, but it's not going to come up in a thermodynamics context. So I'm not going to write it here. Okay, so this would be electrical work. Up here, this is boundary work, and over here, this is electrical work, and they all count. So that's what's going on there. I won't give you a formula for heat changes, amounts of heat yet. That'll involve some other discussions. So, but we will have that. Oh! I need to say some words. Naming this. When you divide, when you divide by mass to make it intensive, we call things specific. Okay, so specific will mean per mass in general. There might be a couple historical accidents where that's not true, but that's what we call. So for example, I would say lowercase ke is specific kinetic energy. And PE is specific potential energy. And lowercase u is going to be specific internal energy. And lowercase w is specific work. And then we get to Q. So any guesses what we're going to call that? Is there a pattern?
Specific heat.
Yeah. Crap. The damn chemists already took that one. So I will call it specific amount of heat. Okay. It turns out specific heat is already taken. And it's actually equal to the derivative differential amount of heat divided by change in temperature. And the symbol for that is C. Okay, so damn chemists, they took my term. So just got to watch your language. That's easier for some of you than others, but and be just, this is a term that we already know about from chemistry. I'm not going to try to reinvent that. Everyone knows it. So I will just be very careful and call this a specific amount of heat. And then specific heat actually refers to how it changes with temperature. Okay, and I can't change that. That's just inherited language. All right. We'll come back to this later, but this is important to know. All right. I wanted to do an example, but this is a long Zoom meeting. So I think I'm going to stop this here. I'll post this video. And on Friday, we'll have another Zoom class like this. And we'll go through an example where basically, hopefully you're watching the videos where you calculate work and you go see how that's done. What we're going to do is go through the first law, one of these versions like this, and excuse me, we will go through and we will calculate the work done, and maybe be given the change in internal energy, and maybe these are 0, and then solve for the heat. So just kind of go through and use this equation and kind of evaluate the different terms, and then figure out what you can, and then use this equation to solve for whatever else you might want to know. And we'll go through and do some examples with that. And the other thing I will do is kind of pick up here where I was talking about how you could divide this differential form by time to get powers. We're going to do that for everything. So we'll have kind of a power version for kinetic energy, power version for potential energy, power version. Basically, it's going to be, it'll be simple. It basically just divide this whole equation by time. But I want to do it and write it down in a way that's in one place for everyone as a reference. Okay, if you haven't been doing so, you need to start reading the chapters. These first chapters especially are just a wealth of vocabulary, and you really need to know the vocab. I'm trying to hit all the vocab that I can. I'll be honest though, like I almost did with specific here at the end, I'm finding that sometimes in these Zoom settings, I don't have my normal flow, and sometimes I'm forgetting some words. So make sure you're reading through the chapters and picking up on the vocab. That's really, really important. Okay. Quite frankly, if you have a really solid understanding of the first law, a lot of the rest of the course, at least up until we get to entropy, are just kind of obvious details. I mean, if you really understand the first law and kind of how the vocabulary, a lot of it is just working through little details, or more kind of obvious little tweaks here and there. All right, so let me stop there. This video is long, and you guys have been on Zoom for a long time. Are there any questions I can answer, or anything that's puzzling? It's a lot of it. Yeah.
I had a question on the lab.
Okay. Yeah.
Could you go through the derivation of that integral again?
Okay.
I got the constant part, but the integral, how did you set the integral up?
Think for 1 second how I did that. Yeah. So on the lab, so we got to a point where I could write I'm going to try to jump in here in the middle and see if you can, if you're to this point, and then we'll see. So if I remember right, we got to a point where it was A1 times V1 equaled A2 times V2, but then we wrote that as the kind of friction fudge factor, and then we had a factor of square root of 1 minus A2 over A1 squared, and then I had a square root of 2G, and it would be the height. Did I call it Z or Y? I can't remember. Maybe Y1 minus Y2. I'm doing this off the top of my head, but if I remember right, I got to that point. Is that okay, or do you want me to start farther back and work up to this?
That was about where we were.
Okay.
When...
Okay. And so let's draw a picture here too. So we had this, and I have a little opening here, and I have an opening here. So this was A1, and the water level was up here, and this was A2, and it was down there, okay? And this relied on the assumption that both were at 1 atmosphere, so the pressures canceled to simplify to get to this point. All right, as it discharges, oh, the other thing is, we're about minus signs here. This is a positive kind of flow out, whereas here, this is a flow down. It's like a loss of volume. So there's a minus sign issue where the right-hand side really wants to be positive. The left-hand side, well, if I want to get rid of these absolute values. So when I do that, I need to put in an extra minus sign. And I think I said that kind of quickly there in class. All right, and it just has to do with when I'm standing here, it looks like I'm losing volume, but over there, I would call that a positive flow outwards. So there's a minus sign there. All right, and V1 is simply dy1 dt, right? Because pick a point here, the velocity at 1 is just the change in height of the water level. Is that okay, Brian?
Yeah.
Okay. So, and it's important here to note, I know I wrote it all symbolically and it looks like y2 and y1 are on equal footing, but note y1, don't mix it together, y1 changes, y2 is constant. So that means though, even though they kind of enter on equal footing here, they're really different from a calculus point of view. Y2 is just some constant, just some number. Okay. And so if we start at some height, y, I call that y initial, and then it goes down to some other height, wherever, y final, as the water level changes. So that means y1 starts at y initial and y1 ends at y final. Y2 never changes. So got to be clear on that. Then what I'm going to do is kind of move all the y things to one side and all the time things to the other side and set up an integral. All right, so I'm just going to do that. So I'm going to get dy1 dt equals minus a2 over a1 times the constant divided by a. Now, if you numerically plug in numbers, the square root thing is basically 1. High accuracy. So you can just call that 1. If you look around the internet, you'll see this formula where they just replace 1.
Your mic's out.
Is that better?
Yeah.
Okay, I don't know. So numerically, when you plug in numbers, this thing in the square root is basically just going to be 1. But in the internet, a lot of places you'll see this formula written where they don't even bother to write it. Okay, but right, it's there. And then I'm just writing all the things which are constant. And then I have square root of y1 minus the constant y2. Just rewriting this. And I'm going to move all the y's to the left, reversing it, and all of the time things on the other side. So I just rewrite this as dy, just play fractions. Okay, you see how I'm getting that?
Yeah.
Okay, And then this is a power law integral. So this is a square root. So I raise the power by 1. So this is a negative half power. It becomes a plus half. And then I divide by the new power. So I divide by half, which is multiplying by 2. So this becomes 2 times the square root of y1 minus y2 evaluated from y1 equals y initial to y1 equals y final. And that equals minus a2 over a1 c square root 2g over square root 1. Answer to 8.
So y initial then just becomes our the
Initial.
heights, the initial height and the final height from our test, right?
Yeah, well, and so you do for each interval, right? You have a whole bunch of intervals from like time 1 to time 2, time 3 to time 4. And so on each interval, you have an initial and a final height, initial, final height, initial, final height.
So you have to do each one
Yeah.
individually?
Yeah, and then you can kind of use that to see how accurately it follows the formula. Yep.
So what should you get if you just go over the whole time?
You could. The thing is, what I suspect is when it gets towards the bottom, it doesn't work so well. So I'm expecting it to work well at the first ones and then not so well.
Yeah, I got some crazy small number. Didn't make any sense.
Check your units. G should be, if you did your lengths in millimeters, G should be in millimeters per second squared. So that'd be like 9,800.
Yeah. Yeah, I did everything in millimeters.
Okay, so just watch your units too. I don't know. So.
All right, thanks.
All right. Okay, I'm going to let you guys go. I got to make sure my kids are on Zoom. Otherwise, they just screw around all day. All right, see ya.